we might as well get started. I'm going to take you, well, we are all going to go today on a journey into the inner workings of the JVM a little bit. Try and give you an initial primer for how to start understanding what the JVM's just-in-time compiler, the JIT compiler, does, and how to get you a little bit of visibility into what your application's doing. So let's go down the rabbit hole. This is me. I work for Red Hat now for the past I think 5 years now. We're kind of in a research and prototyping group. We play around with interesting technology, throw stuff against the wall, see what sticks. One of those projects is JRuby. For the past 4 or 5 years, Red Hat has sponsored the development of JRuby, and we've been very thankful for that. I also work on bringing what we've learned from JRuby to other JVM languages, trying to find the ways to make the JVM a better host for unusual languages like Ruby and Python and other dynamic languages. So this involves a lot of JVM hacking and digging into the internals of the JVM. When I started working on JRuby 10 years ago now, I never thought that I'd be looking at dumps of assembly code from the JVM's JIT to try and optimize Ruby code. But that's the sort of thing that I've had to do, and hopefully what I teach you here today will make you able to do some of that as well. And I'm headiest on pretty much every service, so it should be pretty easy to find me. Okay. So we're going to dive into the JVM a little bit here, and this is kind of an arcane and hidden world from most Java developers. We generally throw code at the JVM. It does something magical to it, runs it, optimizes it, makes sure all of our objects are collected, and we don't look under the covers a lot. But we end up losing a lot of information. We can't see some of the inner workings of the JVM. We can't see how it's affecting our application. And so sometimes you need to go a little bit deeper. And so what we're going to do today, we're actually going to drink the mysterious bottle of JVM fluids and see what's happening down below in the underpinnings of the JVM through a few standard, well, semi-standard flags that you can get some visibility into the JIT. So what are we going to do today? We're going to look at a few interesting, common, typical Java features. We're going to see how the JVM actually compiles them down to bytecode. And I'll have some basic primers on what that bytecode is, but we're going to see what we actually get in the class files for a few common JVM features. And then we're going to go further. We're going to see what the JIT does with those bytecodes and how it optimizes, whether it optimizes them properly, and what we can learn from that information. And we will actually have a look at some of the native code that comes out of the JIT, so you will actually get to learn a little bit of x86 assembly today. So now, why is this an interesting thing to do, first of all? Before we dive in, why would we want to do this? Well, so who are you? I assume most of you in here are some level of Java developer, performance engineers, people that are doing performance analysis on applications, trying to find problems, trying to optimize an application, make it run better. If you're just simply debugging, trying to figure out why your application isn't behaving the way you expect it to. And really, all of us in the Java community, at some point in our careers, we do all of these things. We don't just write code and then throw it over the fence. We've got to profile, we've got to test performance, we've got to debug code. And for all of these, having a better understanding of what the JVM does internally will make you a better developer. The details of all these different things matter. That's what I'm hopefully can get across in showing how these features work under the covers. There's lots of cool features out there that we love using, inner classes and lambdas, structural types in Scala, serialization that's been in the JVM, unfortunately, since the beginning. And how we write code and which features we choose to use have a direct impact on the performance of the application. And by extension, the debuggability of the application, the visibility of what's going on at the JVM level. And we really need to know what the JVM is doing under the covers for all these features so we can make our best decisions about what features to use, how to write our Java application code. There's another talk that I've done in the past that's it basically explains how you can write Java code that's as fast as C. And I'll give you a hint, you don't write it like the Java textbooks tell you to write it. You basically write it like C. And so all the features, even just the basic patterns of writing Java code, have a cost. And we need to understand what those costs are. Anybody heard of the sufficiently smart compiler? This is a concept in the JIT world, or really in the compiler world in general. So there's this sort of verbose description of it, that if you have a high-level language that's built on top of a lower-level language, if you learn enough about that high-level language, eventually you can make that performance gap between the two go away. And when we apply this to the JVM, the idea here is that if you wait long enough, and by wait long enough, I mean let the JIT run long enough, let the profiling happen enough, let the JVM engineers have enough years to work on the JVM, eventually all these performance problems just melt away, right? And we'll get there. It's the sufficiently smart compiler. We don't have to write in those low-level languages because there's no impact to it anymore. And now the problem here is, what's your definition of long? For a short-running application like a developer tool, a long run may be 5 seconds. For an application that's in production, it may be years. You may have the same application running for years. And now we can't say that we're going to ever get to that sufficiently smart compiler unless we know what that time frame is, and unless we can see at each point in time what the JVM has done to optimize how close it is to getting us to the fastest code. Okay, so we'll jump in now. We'll go down the rabbit hole here with a short primer. So I have some vocabulary. Most of these terms you Java developers should all be familiar with. So source code is, of course, the Java code that we actually write, the text files on the file system, and the bytecode is the class files that come out of that. Or at runtime, the bytecodes that are generated by libraries, by dynamic languages, for example, JRuby, by non-dynamic languages or semi-dynamic languages like Clojure that load from source but do compile everything to bytecode. And so this is what the JVM first will start running. Eventually, we want to get down to actually running native code. There's a lot of native code in the JVM itself, for the JIT itself, for the GC, for some of the interaction with the operating system. But of course, our JVM code will also go through the JIT eventually and get into native code. The heap is the JVM controlled area of memory. So generally, this is managed entirely by the GC. We're not just allocating and deallocating memory directly there, as opposed to off heap, the unmanaged space where we actually do manage all the memory. And then JIT, of course, just in time, the compiler that eventually will turn your interpreted bytecode into native code, hopefully speeding it up in the process and optimizing it. And then there's also ahead of time compilation we're hearing about more and more on the JVM, which is essentially compile everything before you start running it. And this may be dump it to the file system and save off a binary like the Java 9 ahead of time compiler does, or this may be immediately before you execute it, compile it down to native code, which is what the Microsoft CLR does. So JVM 101, I think this sort of patterns come up in a couple talks today, so you've probably seen this. So of course we take our Java C and compile Java source into JVM bytecode. That JVM bytecode then will run in the JVM, usually in a bytecode interpreter. There are some JVMs that just have a very simple JIT that they will run as that first execution level. But the idea here is that we do a very quick jump into execution, but we hook some profiling information in there to gather which methods are being called, which branches are being followed, to give better information for optimizing the code later on. Eventually, the bytecode interpretation, if it looks like we've got enough hot code here, we're using it a lot, we'll hand it off to the JIT compiler. The JIT compiler will take that code and the profile information we've got and produce some native code for us. And then most JVMs will have a cycle here where the native code may turn out not to be the most optimal later on. We may end up following a branch that was rarely followed early in the application. We need to make some adjustments here and change what we actually run. So we'll go back to the interpreter and the cycle repeats. Round and round, and you'll see the JIT continue to run forever on a lot of applications. All right, a bit more vocabulary. So inlining. Inlining is the big optimization that we can do with a profiling compiler. If we're able to tell that we've been calling the same method over and over again, well, let's not do the overhead of making that call. Let's pretend that these were written as a single method to begin with. It gives us more visibility into optimization. And then, of course, optimization. What is optimization? Doing the minimum amount of work to accomplish some goal. This is the highest level definition of it. We basically want to eliminate all the unnecessary overhead, the unnecessary execution, the unnecessary instructions in our code to get to that final product. So what does inlining look like for, in this case, an instance method? So if we're inlining a method and we're making the same call every single time, we want to load the target method object or pointer in memory somewhere, whatever the target object is. We want to load the arguments. Now, if it turns out that the target type is the same, well, we know that we're still calling the same method. We can go directly into the code and not have to do the extra lookup process, the extra indirection through some method table. If it is not the same target or something else has changed at the JVM level, well, we go back into the cycle of looking up the method, doing a slow call, and then possibly re-optimize and inline it differently in the future. Now for static, or what are called special methods, which would be constructors and super calls, where the JVM can tell basically at boot time which method's going to be called, there's less overhead here. There's some guards in here to make sure we're not reloading classes, make sure we're not modifying static methods that are already in memory, but the simple case, largely we can load the arguments and just go straight into that static code. And so even some of the simplest JITs can do optimizations on static methods. Okay, and the tools that we're going to be using, everyone's used Java C, and don't need to talk there. How many people have used Java P before? Okay, Java P to dump out JVM bytecode, along with all the constants that are in your class file, the general structure of methods, and so on. We're going to go into a few that you may be less familiar with. Print compilation, which for Hotspot, the standard OpenJDK JVM, will show compilation logs, methods that are being compiled as they're being compiled. Print inlining, which will give you a very rough representation of which methods have inlined into each other. And then, of course, we'll go into print assembly later that shows the native code that the JVM's actually decided to install for this method. All right, down we go. So of course we'll start with the standard place the Java developers start. We'll start with a hello world. Probably the most characters of any hello world in any language in the world, maybe. So here we have our basic hello world, which I think has come up on at least one other JVM talk today. All right, so level one, we'll go down the first level here and see what sort of bytecode we actually get out of this. How many people can read bytecode or have done bytecode generation? Okay, so maybe a quarter of the room. All right, good. So Java P is the Java class file disassembler, essentially. You can dump the basic structure of the class file, just showing methods and fields, but you can also go deeper and show metadata, like which constant values are in the file, what the actual bytecode is, and so on. So if we just run it directly, running it against our little example here, we get kind of a pseudo Java representation of what the class structure is. We have our class name, we have the methods that are in it. In the original code, I did not have a constructor. Java C will generate a default constructor for us that shows up here, and of course our main method. Now this is not terribly interesting unless you just want to look at the basic methods that are exposed. If we add -C, then we actually start getting bytecode. And now we can actually look into what the code is doing, what Java C is doing to our code when it creates a class file. And so these are fairly simple. We'll walk through the basic bytecodes we've got. So we saw get static and put static, which are for retrieving and setting static fields in memory. We have LDC, which is kind of the toolkit for pushing constants, numeric constants, string constants, and so on. Invoke virtual, which is essentially just calling an instance method on some object directly, as opposed to invoke interface, which is through an interface, invoke static, and so on. And then return, if it doesn't have a type prefix, like an I for integer, this is just a void return. And so we go back to our code here again, and we can now read this pretty easily. Get static, we're pulling the system.out field out of the system class. LDC, we are loading our constant string hello world. Invoke virtual, we're calling print line on the print stream that's available. And then we have nothing to return, and it's a void method, so we return. All right, so that level is pretty simple to understand. There's only a little over 100 bytecodes, and most of them are pretty straightforward to follow. Okay, so let's go a little bit deeper and make this a little bit more fun. Well, we'll actually start looking at compilation logs. And I mentioned these two flags before. We're going to first look at the methods as they compile. When the JVM decides this is hot enough to JIT, we'll see a log entry. And then we'll also see some structure for inlining. So let's talk a little bit about how Hotspot's JIT works. So code, in Hotspot there is a first level, a tier 0 essentially, that is the interpreter. And so pretty much every code that loads into the JVM will run through that interpreter for some amount of time. Later on, the JVM may decide that a piece of code has gotten hot enough, it's being used enough, throws it at the JIT, and will optimize that or turn it into native code in some way. So older Hotspot, Java developers that have been around for more than a few years probably remember the client and server flags that we used to have in Java 6 and earlier timeframes. And these were essentially the don't optimize very well, but get going quickly, which was client, used for desktop applications, quick startup time, or the server optimizer, which would take much longer, think about the code more, profile it more, and eventually, we hope, produce better native code as a result. These days we have what's called a tiered compiler in Hotspot, and in most of the other JVMs, in fact. So the tiered compiler has a few extra levels. It has what's called tier 2 or 3, that basically is the client compiler, the fast starting compiler, but still leave a little bit of profiling hooks in there. So we can get to native code, but then make better native code in the future, still do that profiling step. And then the server it'll eventually dump into. But the idea is that we can have reasonably fast startup and still get to fast runtime performance for a large application. So in this case, we're going to disable tiered compilation. If you have tiered compilation on, logs obviously get a lot more complicated. There's more information being dumped out that we're not necessarily interested for this talk. Okay, so here is what we're actually going to throw at the JIT and see what we get out of it. Notice I have a loop here that runs for 100,000 times. By default, the JVM has various levels where it will decide to compile. I believe for the client, the lower level tiers, it's 100 calls. For server, the more optimized tier, it's by default 10,000 calls. So we're throwing 100,000 at this to make sure that it actually JITs it and we actually see the compilation. And then, of course, there's our simple HelloWorld method at the bottom. So here are the flags that we get to use for this. So we're doing xbatch, which will avoid the JIT running in parallel and stepping on each other. Rather than having two threads that will output separate logs, we'll get a single synchronous log of JIT events. I mentioned we're turning off tiered compilation here, and then passing print compilation to get a simple compile log from the JVM. All right, and so we get something that looks like this. This has changed a little bit over the years, a little bit additional information in Java 8 and higher, I believe. But this is all still fairly readable. So looking at the different pieces here, we've got on the left column the number of milliseconds since the JVM started. So it's a timestamp of when this compile event happened that we can correlate to our performance logs or our bottlenecks somewhere in a profile. We have a simple indexed compile count. So this is compile count number 2 may later on be referenced as, okay, it turned out this was not good code. We're throwing out compile number 2 and doing it over. And you can track that throughout the rest of the logic here. If there's an exclamation point, a bang here, that represents that there is some sort of exception handling that occurs in this method. And so there's different decisions that the JVM has to make about how to optimize it. You'll also see this % sign show up in this log. The % sign means that this method was optimized while it was still running. It was actually replaced with JITted code on the executing stack. And in this case, that's the loop in main. That loop actually ran long enough that the JVM decided to optimize it in place without actually leaving the method. And then we get to see the method sizes here, which is actually the number of bytes of bytecode in it. And since different bytecodes have different sizes, this number can be kind of misleading in some cases. So the interesting ones we're interested here are these two. So here we have our hello world, the one that actually prints out hello world, and we have our main method. Now we'd like to actually see inlining and optimization, how the JVM is actually making better decisions. So let's continue on from here. So again, we've got batch and tiered compilation turned off, which in this case, turning off tiered compilation basically only uses the server compiler, the really strong optimizations. We've got our print compilation. We also have our print inlining, but because this is not typically a flag that most developers are using, you have to unlock it with the unlock diagnostic VM options flag. Now the funny thing is, if you run without that, it says, wait a minute, you need to turn on unlock diagnostic VM options, which begs the question, why don't you just turn it on for me? So you'll get that message, you'll know what to do, but it's a strange flag that we have to pass to turn some of these things on. And then, of course, there's our regular code for the hello world. Okay, so now we get a slightly different output here. We've still got our compile lines largely as they were before, and here's our methods that are interesting. So we see our hello. There's not a lot of code to inline into this, but we've got the print line is there. We make the print line call enough that that actually does inline. And then we also see down below that hello has now inlined into main. So we know that these methods have been determined to be largely a constant target. We're calling the same method all the time. And the JVM has seen fit to inline these together and make one piece of native code. And of course, these are fairly small graphs. The JVM by default is only going to inline about 9 levels. So for a larger application, you're only going to see 9 levels of calls that will inline. It also has other thresholds, for example, for recursive calls. If it's a self-recursive call, I think it only will inline 2 levels, because otherwise it's wasting a lot of time to inline all those recursive calls. But you can throw this at just about any application, find your method in there, see what's being inlined, and see what's not being inlined, which may be the more interesting piece. All right, so let's go another level deeper. We can see that the JVM is compiling code. We can see that it's optimizing code. We want to see what's actually hitting the CPU and whether it's optimized the way we expect it to. So the flag we use here is the print assembly flag for Hotspot. This dumps basically an assembly output in a human readable format. It tries to mark it up to say, okay, this is line so-and-so in your Java code. This corresponds to a particular bytecode like an A load or I load. And this one actually requires a separate plugin. This doesn't ship with the JVM, with OpenJDK by default. So if you Google for Hotspot print assembly, you should find builds for various operating systems and platforms, and you can throw it in. All right, so here we go. I'm actually looking at assembly code for Java now. Again, this is a diagnostic option that we have to enable. And then we have our print assembly. The print assembly plugin is basically just a shared library that you dump into the JVM directory, so there's nothing additional needed for that. And then we run our application. Okay, now for this simple, this Java 101 example, hello world, we get thousands and thousands of lines of output for that one method. There's just way too much code in print line, in all of the I/O operations. It's not a useful target for us. In this case, the server compiler produced about 2,700 bytes of assembly that we'd sit and have to read through to figure out which pieces are interesting to us. Even the client compiler, the non-profiling compiler, still had 594 bytes because it's trying to make guesses based on the shape of the code. So it has multiple versions of the code and multiple different paths it follows. Most of the output that you see, though, is from inlining. We get print line that inlines. Print line calls a bunch of other methods in java.io. Those eventually will call native stuff and stop inlining. But it's just a lot of overhead, and we can't read through all that. So we're going to do something a little bit simpler here. So here we have a super trivial benchmark. All we're going to test is calling the tiny method that adds 2 literal values 1. Now, the first thing that any astute Java developer might know is that the Java-C compiler is at least smart about statically optimizable things like 1 + 1 here. And when you look at the bytecode, you actually just have a method that returns 2. It doesn't actually do an add operation every time. Now, if we were pulling one of these from an argument or from a field somewhere in memory, of course, we need to actually do the add at runtime. But in this case, we can actually just turn it into a value 2 and return it. So already the method's gotten a lot simpler. So if we look at our inlining log here, we've got our tiny method that JITs, very small, 2 bytes, because all it's doing is loading the value 2, which is a single bytecode, as shown here, iconst2. And then we have our main method, which is 19 bytes for the loop itself. Then it inlines the tiny method, and we've got it all in one. Let's take a look at what the assembly looks like. There it is. Everybody here can read a x86 assembly, right? No, I would not expect that. So we'll walk through this piece by piece. Now, before I get too into depth in this, the interesting pieces that we have in this slide are actually just these 2 lines. So here we have moved the value 2 into the EAX register, and at the bottom we do our return. This is the actual code that corresponds to what we'd expect from our little tiny method. What is all this other stuff? So let's actually look at the full inlined version of this, the long version of this code, which gets even more complicated as far as assembly. But a lot of this visual noise can be swept away. So we'll go through a couple iterations of cleaning this up to make it a little more readable. So first of all, we'll shift some of the comments around, remove some of the extra boilerplate that's trying to give us some hints into what the code does. And we've got a little bit more readable code here, straight line list of assembly instructions and their arguments. Now there's some lines here, move, push, sub, and add in a pop at the bottom. These are not interesting for us to look at the actual optimized Java code here, because these are working with the native execution stack. So we're pushing a frame on the stack, popping a frame off the stack. We can remove those for our discussion here. So next we've got these unusual test operations that don't seem to be doing anything. Well, these tests are actually the JVM safe points. These are where the running code, the native code, asks the JVM, is there something I need to do here? Should I garbage collect, or should I pause the thread, or whatever? That's what these are. And these are, of course, interesting for profiling, but for trying to see what code has resulted from our simple benchmark, we'll sweep those away for the moment. And now the next one is this seemingly useless call here to exchange AX and AX. Doesn't seem to do anything, right? Well, it doesn't. This is actually just how we encode a no-op. And I think I believe the no-op instruction in x86 and the exchange AX and AX are essentially the same code at the assembly level. So this is a no-op. Why is it here? It's here to align instructions so that we're aligning it on, say, a 32-bit or 64-bit boundary, helps the instruction decoder work, so we don't need to really look at this one either. And so now we get down to a fairly simple amount of code. So now we'll actually remove some of those those verbose 64-bit addresses, and we've got our move, jump, and so on. We can correlate these back to our code. So at the beginning, we move 0 into some variable. That's the initialization of our loop. We jump down to the bottom, and this is an interesting thing. The first thing we do is actually jump to a test. The test at line 4 here, or at instruction 4, we compare that variable with, I've got differing numbers here. So it's 100,000 in the code, it's 1,000,000 in the assembly, but it's supposed to be the same number in both. We compare it with our terminal condition. If it turns out that we're not there yet, we jump back up to 3, increment that variable, and that's our loop, essentially. Now, you might also notice that this loop doesn't actually do anything. Where did our to go? Where did our tiny method go? Well, that to value was never used, and so the JVM decided to not even bother with it. We don't need to load a to into any variable and then immediately throw it away. Now, if you actually let this run further and on different JVMs, you'll actually see that this is basically the assembly code you get out of the entire thing. The loop does nothing, the main method returns nothing, and the tiny method just returns a literal value that's thrown away. All we do is return here, and the function doesn't actually do anything. So it's not too hard to parse this stuff out once you know what all these pieces are, once you know what the boilerplate is. Okay. So now let's look at some actual JVM features and try to get into some more fun details for you folks here. So these are the ones that I'm going to try and cover in the, I guess, 20 minutes remaining? Yes. We're going to talk about final fields. We're going to talk about the various synchronization mechanisms used in the JVM. We'll talk about the string switch that was added in Java 7. And then we'll talk about lambdas in Java 8 and how they end up looking. All right. So first of all, final fields. Of course, we all know final fields can't be modified. Can't should be probably in quotes there, because you can do just about anything you want at the JVM level. But generally, final fields can't be modified or expected to not be modified. And the compiler can take advantage of this. If it sees that you're constantly accessing a final field, it may not go back to memory all the time to get that value or retrieve it. It may insert it directly into the code. It may be able to make decisions about how to optimize. But it doesn't always, as we'll see here. So here's two different versions of a static final field. The first one is initially initialized directly to a literal value. We've got this is a static string. And for folks that well, we'll wait for the next slide here. So we've got that version that's actually a literal assignment in the static final. And then the other one that is sort of a dynamic final, what I think John Rose calls a larval state. Before the final has actually been applied, there's no value there. We go out and get a property for it, and then it becomes effectively final at that point. And then we'll just print these out and see what we actually get. So here is the bytecode we get from these two. And what you'll notice here is for the directly assigned, the directly initialized string, it actually just loads that string every place. It doesn't go and retrieve it out of some static field every time. Anybody who's dealt with Java C and static constants that are floating around your system has probably run into this. If you modify a constant that's used everywhere, that's initialized like this with either a literal string or a literal numeric value, Java C inserts that value directly into every single class file. You need to recompile all of the places that it's referenced because it doesn't go back to it. On the other hand, the one that's initialized dynamically, this one it does actually have to go and get every time because, as I said, it initially starts out uninitialized. We need to run some code to initialize that field. Not sure quite when that happens, so the bytecode needs to get it right away. So let's see how we can actually do some optimizations based on this. So in this case, we're actually going to do something with these two strings. We're going to add their hash codes together. So here's what we get at the assembly level for these. We saw what the bytecode looks like. So we've got our direct reference to this is a static string. This is just going straight into memory where we know we've got this string object. And since we know that we've got the same string object every time, it's able to do a much quicker access of the hash code. It doesn't have to go through the object. It knows what this was calculated as, the standard Java hash code for a string. The dynamically loaded one, however, here, we do actually see it get the literal string. Now, it's not going out and grabbing this off of an object in memory. The JIT has seen that even though this was a dynamic final, a lazily allocated final, it ends up being the same to everyone that sees it. Everybody sees the same value because it's initialized once. The JIT, I think as of Java 7, will actually optimize this to just a direct load of the string now. It does not have to go through the field. But we do still have to go and get the hash value out of that string object, so we don't get all of the optimizations that we would normally like to see. And this is certainly something that can be improved in the future. So let's take a look at instance fields instead of static ones this time. So here we have a final myString that is initialized immediately to a literal string, and we have one that's dynamically initialized like our other example. So at the bytecode level, we actually can see that the instance string that's directly initialized, within an instance method, it will put the actual string. It'll put the string rather than the field access because it knows, based on Java standards, Java conventions, that once this string is initialized, it shouldn't change anywhere. We can actually just access that value, and it works pretty much like it did before. But it does still go and do the hash code call to get the actual hash code out of it. And then, of course, the one that's dynamically initialized, we do have to get that string every time, get that field every time, and then do our call to the hashcode method. Now, at the native level, our instance string, again, becomes a constant, which is great. So we've got a final field that's initialized to a literal string. The JVM does turn that into a native load of the actual string. But the other one ends up being a get field all the time. Even though we know it's only ever going to be initialized to a single value, because the JVM can't see through that initialization, can't tell that you're only initializing this value once, can't tell that the get property doesn't fail, it still has to go and get the field every time. So here, by poking around in the assembly level, poking around in the bytecode level, we've found something that Hotspot could do better. If a final field is lazily initialized, Hotspot probably could do a little bit more to inline that value. Okay, so concurrency stuff. We'll talk a little bit about synchronized and volatility here. So here's a quick example that has a non-synchronized and a synchronized version of just going and getting the current time. If we look at this at bytecode level, the interesting thing when you first look at bytecode level, you don't see any, so there's no synchronization code here. There's no bytecodes being inserted for us. Funny thing, when we go to the actual synchronized method, there's still no bytecodes that are inserted for us. This is just a flag on the method, so that the JVM knows when it enters a method that is marked as being synchronized, we need to do that synchronization for the code. If you actually had a synchronized block within the JVM bytecode, then you would see the try and an exception handling logic for locking the object, running some code, and then going back. But with the synchronized keyword, the JVM does that under the covers for us. Let's look at the assembly code. So the non-synchronized version is fairly simple, of course. All we're doing is moving the system class somewhere that we can access it and then calling the current time millis static function on it. What does the synchronized version look like? Well, I'll tell you, it's a lot bigger. There's a lot more code that's output for this. Here is our actual interesting bit at the bottom, where we're essentially doing the same thing as the unsynchronized version, just calling current time millis. This preamble code basically has to run all the time. This is the minimum amount of work that the JVM can do to handle that locking. Now there's a little more vocabulary needed here. So there's a couple features in the JVM's JIT and in other JITs that improve the cost of locking. So lock coarsening, which I won't be showing today. Lock coarsening is if you are locking the same object repeatedly within a given piece of code, the JVM will try to condense those together. It'll lock it once, do all of those operations, and then unlock it, rather than having that preamble lock code every single time you lock the object. It can also do some lock-eliding, or reducing the cost of actually doing the locking itself. And this is when it sees that the lock is not necessary. For example, if you have an object that is only ever seen by this thread, never returned from this method, you don't need to synchronize on it. No one ever is going to see that code. No one's going to modify that object concurrently. So we go back to our assembly dump from the synchronized version. And you'll see that after doing some juggling of stack and other things, we've got a jump here. So this jump is actually where we go into the locking code. The JVM basically has a bit on the objects that says, okay, this object has been locked by this thread. The first few lines here are testing to see if we've already locked this object. In Java, locks are reentrant. We don't block if we try to lock twice. So we want to make sure that we haven't locked it already. Now, if it's been locked by another piece of code, we continue right past this jump, do some additional bookkeeping, and then we can get to our code. If we have to do the jump, however, we actually need to do the locking. Then we jump way down in the generated native code and eventually find our lock instruction at the assembly level. And this is the one to look for in your assembly dumps. Most of the time, performance problems are going to be allocation related. When they are execution related or related to the code the JIT's producing, lock very frequently comes up as one that's causing you problems. And I'll show in the next section here how that actually affected JRuby. All right, so volatile. So folks have hopefully gotten a little bit more informed about what volatile means in Java. But the general idea here is visibility of changes across threads. We want to make sure that a write in this thread is seen immediately by a read in another thread. We need to order those operations. We need to make sure that there's no inconsistent views of memory. And so we tell the JVM that these operations on this field are volatile. We need to make sure that they're published across to other threads, and other threads see them on a predictable schedule. And now at the JVM level, this is generally implemented very similar to how locking is implemented, but the performance impacts can be somewhat different. The case that I ran into in JRuby, JRuby's class hierarchy has what's called basic object at the top. Ruby basic object is our implementation of that. And I couldn't figure out, we made some changes to our code and suddenly everything was much slower, like 50% performance on all the benchmarks that we run. Could not figure out why by looking at profiles, could not figure out why by running instrumentation, running samples, just was no indication of what we'd broken. So I actually had to go to the assembly level. So I threw the assembly plugin at this to see what the heck changed in our application. Why is it suddenly so slow? And like I mentioned, this bloody lock instruction shows up in there. Now, I know for a fact that this default constructor for Ruby Basic Object does nothing. Why is there a lock operation happening in there? It's not synchronized. It's nothing like that. Turns out that this change was not such a good idea. If you have a volatile instance field on your object and you're initializing it to a specific value, in this case a null object array, I didn't want to have to constantly check it for null every time I went back to this volatile field, well, you are forcing that object to do one or more volatile writes every single time that object is created. It's unfortunate that we have this cost, but in our case, it actually turned out better to just leave the null checks in. Let the JVM optimize around the null checks rather than doing that volatile write every time. So this is a case where the pattern of pre-initializing an object to avoid null turned out to be the worst possible decision for our code. And basically, almost no profilers would show this. They would never show this in most of the typical profilers. I'd like to see if any of the frame graph stuff could actually show that we're doing too many volatile writes in this case. It was very hard to find, and I had to go to the assembly. So there you go. That level up, and I actually fixed a major performance bug by finding one instruction in an assembly dump that shouldn't have been there. All right. Gonna have to rush through a little bit. So string switch, hopefully most folks have gotten around to using this, and we're happily using it in JRuby now that we're Java 7 and higher. So let's talk about a normal switch. So a normal switch, we have a variable parameter that's passed in and a bunch of constant values. And Java-C will create a table of all those constant values and ideally just jump to the right one when we enter the switch. So a simple example here, how many args were we passed? Let's just print out the string version of that and say how many arguments were passed in. If you look at this at the JVM bytecode level, we'll see either a table switch or a lookup switch in the bytecode. The table switch is used when the values are largely close together within some range and contiguous. So we've got a simple range of values that we can look at. All right. Here's an example of one that compiles down to a lookup switch. So these values are far apart. There's no easy table that we can build just based on these. So this ends up being a lookup switch. You'll notice that these are ordered now. These are sorted. Lookup switch will do basically a binary search internally to find the right branch to go along. And so now our table switch, which is constant time branching, has turned into a log n complexity of branching. So important to know when you're doing your switches that some of them are not going to be constant time. All right, and I just talked about that, O of 1, log n, etc. All right, so the point here. So what kind of switch do we use for strings? Well, we can't just use a table because multiple strings may have the same hash codes, right? The lookups might collide, essentially. So the answer is that we basically do both of these, and we have an equals call to make sure we're working with the same string object or the same string content. So for a switch like this, here we've got several different languages and different ways of saying that we love them. If you look at this at the bytecode, when you actually run this through Java-C, you'll see most of the stuff that you expect with our switch and our hash code call and so on. But there's also this hidden integer variable that it adds into the code. So looking at the lookup switch here, we've got all of our different language names represented as their hash codes. We can do this because the JVM specification says this is how strings hash, so we can actually embed it into the bytecode and create a jump table based on that. So we find our language name's hash code, and then we jump. Let's follow the Scala path here. So the Scala path then will double check, make sure we've actually got the string Scala by calling equals. And then, now we're actually storing a 1 into that hidden integer variable. So now we're basically saying we've found which case this is, we've found which branch to take, and we do another switch. So we load that value back out of the temporary variable. Now we've got a simple table switch. In this case, 1 is the Scala path, and you'll see the line or branch to 167, which is the Scala I love you, I think string. Now, if you want to go take this and back to Java code, and I think some of the Java decompilers will do this if you run Java 7 string switches through them, it's basically this. You could write this by hand, and this is exactly what the code would be produced. So we're embedding the hard-coded version of all of these hash codes. We save off the number of the case that we hit, and then we can do another switch at the bottom to branch into it. So this is important to know. The string switch adds a significant amount of size to the code that you write, and that will in turn affect profiling and affect optimization. The bottom line, though, is it's basically a hash table. So treat string switches as essentially a hash table implemented in bytecode. All right, and the last section here. So Lambda expressions. Sadly, we can't use these yet in JRuby because we still support Java 7, but we're getting there. We'll probably be switching to 8 soon. So the key goals here, this was something to basically replace inner classes, to give you something like inner classes that had both less boilerplate code in your source and was lighter weight at the JVM level. So here's a simple example. We've got a couple different language names, and we're going to do some operations against them. We'll look at sorting first. So for sort, we do collections.sort. We take our input list of strings, and we give it the integer comparison operation to compare. In this case, we're just sorting them by the length of the string. So we'll run this through our bytecode compiler. Do sort here, now in bytecode, and we see there's an invoke dynamic call. So the way that we got around creating extra classes on the file system, like inner classes, creating new objects every time, the Lambda support actually uses invoke dynamic to lazily create essentially that same inner class object that it did before. Rather than having it in the jar file, rather than having that object in memory, we call invoke dynamic. It creates this one-time implementation of our interface, in this case comparable, or comparator, implementation, and then stores it and saves that forever. So we only do this once. And as a result, we reuse that same comparator implementation every single time. We lazily bootstrap it, shove it back into the code, and then use that object every single time. If we look into the bootstrap, the part that actually creates this, there's something called Lambda Meta Factory. This is what's creating the implementation of your interface. So we create the interface implementation. We actually just use this hidden method called Lambda2 to represent the body of that implementation. And if we look at Lambda2, well, this is our sort logic. This is the actual Lambda body that we passed in. So now, how well does this optimize? Have we gained anything optimization-wise by moving to lambdas? Well, so let's look at the problem here. So the problem is that in order to inline code, which is our first step for optimization, we need to have a consistent target method. We need to call the same thing every time. We need to have a direct path through the code. There can't be lots of different ways to go through this code and get to different targets. And now let's look at collections.sort. So collections.sort has a lambda passed into it, and it calls that lambda as a callback. So we're going to see many different methods. Pretty much every lambda in the system is going through collections.sort, and will be called against lots and lots of different paths. It ends up looking something like this. There's no easy way for Hotspot today to optimize sort for all of these different call sites, for all these different callers and lambdas. There's no way that it can say this path goes always to this particular lambda call. So we've got two versions here to demonstrate the performance impact of this. We're going to map these strings based on their initials and then join those all together. Here is a different version that doesn't use the utility methods. It does both the map and the collection of the strings together as a manual step. So essentially I've hand inlined the map and collect implementations here. Okay, so here are our lambdas that we've got set up, and we're going to run our benchmark. So there's the basic bootstrap for it. And let's see what we've got. So if we look at the get initials, which is using those utility methods, we can see that all of the utility method calls themselves do inline. The map call inlines, the collect call inlines. All of this stuff actually does inline at that level. But once we get inside there, we can't inline any of those lambdas. So our biggest tool for optimizing Java code now goes out the window because we've decided to use lambdas. Sadly, another case where Java code has not been kept up with by the JIT compilers. JIT compilers just do not optimize this well, and this is going to be more and more of a problem for JVMs that don't specialize that sort and don't make it possible to optimize through. So for the short term, what we have to do is we basically specialize it ourselves, make our own version of the sort or map or collect or any of those utility lambda functions. And that's what the get initials manually here is doing, appending all those initials together and then printing out the string. So this one, it actually does inline all this stuff. We can look down at the bottom where we create our final string for the whole thing. We can see that our get initials manually method is there, our lambda methods are there, and our substring methods are there, all together inlined properly. This is what you have to do right now to get lambdas to inline correctly. You cannot use most of those utility methods. So that may or may not affect your application, but it's something that you need to know about. Okay, we're just about done. We'll wrap up here. So what have we learned? So the JVM is an amazing platform. We can generally just throw code over the wall. The JVM takes it and optimizes it and does all sorts of wonderful things with it. But we all know that it's not perfect, and there are cases where this falls down, doesn't optimize the way we want it to. Well, hopefully we've also seen that every feature that we choose to use has a cost, and we need to know what that cost is. Knowing the cost of all these features, you'll be a better developer as a result. And if, like Alice, you aren't afraid to go down the rabbit hole. Thank you. I think we started a little late, but do we have time for any questions? Yep. Questions? Comments? Insults? All right, feel free to grab me. I'll be around. Thank you.